Hello everyone, we'll be studying applications of Bernoulli's equation in this session straight away. It will be Venturimeter, orificemeter and Pitot tube theory and proofs or derivations of the equations as far as these meters and tube is concerned. We'll straight away go ahead. Venturimeter. Venturi is the name of a person who invented this particular meter. That's why it is in his name that it is called Venturimeter. So here there is a pipe, the flow is occurring through that, and then if you want to measure the discharge of the pipe, then you have to use what is known as Venturimeter. How it will be, you have to cut the pipe in between and insert in between a Venturimeter. It will be fitting exactly to the pipe diameter on both the ends. So Venturimeter comes in such sizes that fits exactly into the pipe that you want to fit in. Right? So diameter of the pipe, if you observe here at the inlet, here at this point, or at the outlet, it is exactly matching the pipe diameter. So you have to cut the pipe and insert it exactly. There will be, of course, fitting arrangements over here. So what you are observing here is Venturimeter. What are the main parts of Venturimeter? What is the purpose of Venturimeter? If you look at Venturimeter, is a device for measuring discharge. It doesn't measure velocity. It is directly giving you this discharge, that it will be so many centimeter cube per second or meter cube per second. Of course, it's a homogeneous equation. You can use the equation in any units. Right? What it consists of? It consists of inlet or convergent cone. So here there is a convergent part, means this particular part is convergent part. There is a throat, a small portion having constant diameter actually, right? And then afterwards there is an outlet which will be increasing in its size, right? So it will be diverging part, right? What you can observe here is the length of convergence is less than the length of divergence. Because of that, the Venturimeter cannot be used the other way around. Means you cannot apply the flow this way and try to measure the discharge. Make a note of this, right? Always smaller convergence end will be inlet end, and longer diverging end will be on the downstreams or at the outlet. Okay. One more thing that you should observe here is there are tubes or piezometers which are attached at the entrance level. We call it as section 1, and at the throat level at section 2. Here, as there is a convergence, the velocity will be more, obviously. As the velocity increases, the pressure drops down. You can just see here. Here there is a pressure right up to this level. Here the pressure is only up to this level. There is a drop, and this drop is only because of the pressure difference. And the pressure difference is because of conversion of kinetic energy into pressure energy. Okay, we'll see further. The same Venturimeter is shown there. The inlet section of the Venturimeter is same diameter as that of the pipe to which it is connected, that you have seen, followed by the short convergent section with a converging cone angle 21 plus or minus 1 degrees, and its length parallel to the axis is approximately equal to 2.7 times d minus d. Now capital D indicates the diameter of the pipe, the lowercase letter d indicates the diameter of the throat. So this difference d minus d multiplied by 2.7 would be the length of convergence. Okay, and its angle, what it means is the if you extend this, I mean whatever convergence is there, if you extend this and then if you extend this also, the angle created over there will be of that magnitude, that is 21 plus minus 1 degrees. Yeah, I have taken it out. Here if I extend this, the angle made over here is of the type 21 plus or minus 1 degrees, right? A converging angle, where d is the diameter of the pipe, lowercase letter d is the throat diameter. Okay. Next, the cylindrical throat is a section of a constant cross-section with its length equal to diameter d. The flow is minimum at the throat. The flow is having a minimum cross-sectional area, not the flow itself is minimum. Usually diameter of the throat is half the diameter of the pipe. Means here what they are trying to tell is this lowercase letter d, which is diameter of the throat, is equal to the capital D, the diameter of the pipe, divided by 2. And moreover, this is a constant diameter section, which is a throat, where there will be a pressure tapping. Here also there is a pressure tapping. Next, a long diverging section with a cone angle of about 5 to 7 degrees, where in the fluid is retarded and a large portion of the kinetic energy is converted back into pressure energy. If you take it out and then if you extend these sides, whatever sides are there, extend, right, whatever angle that is made over here, this angle is quite less. This is only 5 to 7 degrees. You can just see here. So that's an important information, 5 to 7 degrees, where this is around 21 or 22 degrees. So this is opening up quite large. Here it is opening up quite less, right? The angle is quite less. So that's why to reach that same diameter D, it takes a longer distance, whereas this comes quite sharply, right? So that is an interesting thing that one should remember. The flow can occur only in this direction. You cannot supply the flow this way, or you cannot change the direction of the Venturimeter and use, right? Okay, principle of Venturimeter. On what principle the Venturimeter works? The basic principle on which the Venturimeter works is that by reducing the cross-sectional area of the flow passage, a pressure difference is created between the two sections. Section 1 and 2, the sectional area is reduced. Because of that, there will be a pressure difference. This pressure difference enables estimation of the flow rate through the pipe. That's all. So there will be a reduction in the cross-sectional area. There will be development of pressure difference is created between the two, and this pressure difference enables the estimation of the flow rate through the pipe. Okay, this is principle of Venturimeter. Now there is a derivation. expression for discharge through Venturimeter. So here there is diagram, section 1, section 2 having constant diameter, you can see, and very prominently this is a converging very small length, whereas this is diverging to reach the same diameter as earlier in a larger length. And here there is a pressure tapping, it is attached to this point. Here there is an inlet, at the inlet also there is a pressure tapping, and in between you will be having, actually there will be a U-tube manometer for this. So you will have U-tube manometer attached to these two, and the difference in mercury level is given as X, right? We can draw this slightly in a different manner also. Very small length also it can be drawn. Here itself it is joining, let us say. So there is mercury in this wall. It has started from here, it has gone up to that point. Now here you can just see here the pressure is more, because of that the mercury is being pressed down, and here mercury has gone up, in the sense the pressure at point 2 is less, but the velocity at 2 is quite larger. That is because total energy at section 1 should be equal to total energy at section 2 because of Bernoulli's principle. Anyway, we'll apply that principle and then try to see how we can get this final expression of actual discharge. Okay, let D1 be the diameter at section 1, D1, P1 be the pressure at section 1, V1 velocity of the A1 cross-sectional area at 1. So at 1 you got area A1, velocity V1, pressure P1, diameter D1. Similarly, at section 2 we'll have D2, P2, V2, A2 be corresponding values at section 2. Now, most important thing is applying Bernoulli's principle. Bernoulli's equation at section 1 and 2, we can write P1 by gamma V1 squared by 2z plus z1 equal to P2 by gamma V2 squared by 2z plus z2. Because 1 and 2 are at the same level, z1 is equal to z2, right? Hence it is P1 by gamma plus V1 squared by 2z plus P2 by gamma V2 squared by 2z. Now if you take P2 on this side, P1 by P2, P1 minus P2 by gamma equal to V2 squared minus V1 squared by 2z. This is nothing but the pressure difference between point 1 and 2. That is nothing but pressure difference in terms of X. If we call it as H, pressure difference in terms of water. So where H is P1 minus P2 by rho g is the pressure difference between section 1 and 2. Okay, so that is one important step that we have done, that H is equal to the pressure difference is equal to this. But what we know from continuity equation is A1 V1 equal to A2 V2. Because of that, V1 can be written as A2 V2 by A1. Now this H can be written in terms of, look at this, V2 squared by 2z, but V2 squared by 2z you can keep it as it is, so V2 squared is kept as it is, V2 squared minus, now instead of V1 we'll have to substitute this, which is A2 squared, okay, V2 squared divided by A1 squared. So this is what we get H equal to. Now if you take the LCM, it will be A1 squared at the bottom. That's what they have done here. V2 squared is taken out. That's what is done here. So this becomes A1 squared minus A2 squared. It should have been A1 squared minus A2 squared here. Okay, that's how you get this expression H equal to V2 squared by 2Z in the bracket A1 squared minus A2 squared divided by A1 squared. So this, from this one can write expression for V2 because this 2GH can be taken on this side, so that you will be having 2GH. Also there is A1 squared is equal to V2 squared into bracket A1 squared minus A2 squared. That bracket is there. Now from this, if you want to write a V2 expression, obviously you have to take the root. That's why this becomes simply A1, this becomes root 2GH, and this bracket will be under root A1 squared minus A2 squared. Now with all this information, substituting the value of V2, because we have got V2 here, V2 in the equation Q equal to A2 V2, because the discharge is given by A2 V2. We know A2 because it is nothing but cross-sectional area. So Q theoretical becomes the velocity, which is A1 root 2GH divided by A1 squared minus A2 squared multiplied by A2. That gives you this. So this is a theoretical equation for calculating discharge through Venturimeter. But there will be some pressure, energy drop between section 1 and 2, so this value will be slightly more compared to the actual value. To match it to the actual value, there is a multiplier which is known as coefficient of discharge. So above equation is for ideal fluids and is called as the theoretical discharge equation of a Venturi. For real fluids, the equation changes to a multiplier CD, which is known as coefficient of discharge. Right? Otherwise, the equation remains the same: A1 A2 root 2GH divided by A1 squared minus A2 squared. This will be H. The value of CD here, here only convergence loss is there. Because of that, this coefficient of discharge will be very high, in the sense hardly there is any loss, so to say, almost equal to 1. It can be 0.98. Almost all the time it will be of the order of 0.98, 0.99. Rarely it will be lesser than this. So with this we can calculate actual discharge. So look at this. Now what you want, knowing the diameter of the pipe, diameter of the throat, we can work out everything here. The only unknown that we should worry about is this H. What is H? H is the pressure difference. This particular term, H, is the pressure difference between the 2 points 1 and 2, and here it is indicated by mercury level difference X. So X is not directly taken as H, you have to convert because it is a mercury, whereas H is in terms of water or in terms of the liquid that is flowing into the Venturimeter. Okay, here orificemeter. Anyway, before doing this, I would like to give you the conversion between H and X. I would like to write here, this H will be given by the X into bracket SM that is manometric liquid specific gravity, divided by S, that is specific gravity of the liquid that is flowing here, which is S. Here manometric liquid specific gravity is Sm. Not necessary that it is mercury, but whatever manometric liquid that I have used, Sm by S minus here 1. That gives you the expression for H, which is used over here. So this H has to be substituted in terms of X as X into bracket Sm by S minus 1. Okay, with this idea we'll go further. Orifice meter. Yeah, this is orifice meter. Now what is it? It is a device used for measuring rate of flow through the pipe. Means exactly the same application as Venturimeter. It is a cheaper device as compared to Venturimeter. The basic principle on which the orifice works is same as that of Venturimeter. What is that principle? You have to decrease the size. There will be a pressure difference. That pressure difference helps you in calculating the velocity, and that velocity helps you in measuring discharge, right? So it consists of a circular plate. Look at this. Here there is a, if you look from the front, how it looks is quite simple. I'll draw a picture here. The pipe diameter is something like this, and then if you see this one, it will be having a hole like that. That is an orifice. So this is sharp edged. You can observe this. So when the flow occurs, right, it will be touching least part of this. So that's why, right, it will not be the other way around, right? It is sharp edged like that. One edge, there will be another edge which will be like this. So the water, when it moves like that. Of course it covers all the area here, which will be because of the eddies and all, but water shoots that way and then occupies everywhere, right? So there is a circular plate with concentric hole, which is a orifice, right? You know that what is orifice is nothing but a small hole. So here in the pipe there is a circular plate which is fitting into the pipe. Then there is a concentric hole having same diameter d naught or area a naught, right? So this area is this A1 area is nothing but the pipe diameter. Anyway, the diameter of the orifice is generally around 0.4 to 0.8 times the pipe diameter, means approximately half. That's what it is. One more thing that you should observe here is there is a differential manometer which is attached at this point, right, soon after orifice, and then before you have got attachment of this differential manometer, and then this manometer has got some manometric liquid, right, and difference in manometric liquid is X. Again, once again, the specific gravity of manometric liquid is Sm. Specific gravity of liquid which is flowing into this is S. Then this H is given by X into bracket Sm by S minus 1. That will be making this H. Otherwise the expression is exactly similar to Venturimeter. Only thing is here area of the orifice is called A naught. A1 is nothing but area of the pipe. That's all. That's the difference. CD is there, coefficient of discharge. Otherwise expression is exactly same as Venturimeter. Okay, the last one is a Pitot tube. What is Pitot tube? Pitot tube is a device used to measure the velocity of flow at any point in a pipe or a channel. Look at this. Venturimeter and orifice meters are the devices used only to measure the discharge through the pipes. Here Pitot tube can be used in the pipe or in the open channel also, right? The principle behind this Pitot tube. Pitot is once again a name of a person, right? If the velocity at any point decreases, the pressure at that point increases due to the conversion of kinetic energy into pressure energy. That is Bernoulli's principle. Means this depends upon Bernoulli's principle. In simplest form, the Pitot tube is consisting of a glass tube bent at right angle. So whatever pink tube is there, which is bent and then it held with its face as if the flow is entering into that. If you hold the other way around, nothing happens, right? So rather you will not be able to get anything. This tube has to be kept open so that the entry of the flow occurs, right? So what you can observe here is there are 2 points indicated, maybe section 1 and section 2. The pipe has started at this point, Here at section 2, the flow is coming. It has got some velocity, but at point 2 what happens is once the flow has entered up to this level, all this is stagnant. It is not moving. Even at the point 2 over there, the flow is not happening, right? But earlier point, the point 1, the flow is occurring and it stops. This is called stagnation point, means the particle of flow comes to stagnancy, that it stops, right? Okay, we'll go further. Okay, here let P1 be the pressure at section 1. Okay, 1 that is section 1, that is section 2, right? P1 velocity, P2 pressure at section this is P1 pressure at section 2, printing mistake, velocity at section 2. H, the depth of the tube in the liquid, this is shown as open channel flow. Let us say a rise of the liquid in the tube up to the free surface, means here inside also there is a free surface. Let's say this is also free surface, so above the free surface or up to, right? So you can use this part above also, above the free surface. Okay, so the tube is inserted in such a manner that the flow is directly entering into the tube. Okay, you have seen this, what is Pitot tube. Now applying Bernoulli's equation, so application of Bernoulli's equation, it is what we are doing is section 1 and 2 usual P1 by gamma V1 squared by 2z plus Z1 equal to all corresponding at 2. But because section number 1, right, section number 2 are at the same level, Z1 Z2 cancels off, right? And as I told you, at point 2 V2 is 0, that is stagnant, right? Now total head at point 1 will be nothing but H. Head at point 1 is H only, because here it is h, and it has got some velocity v1. When it comes to point 2, here it has got head of h plus h, but velocity is 0. So now corresponding application, let us, substitution will do. For P1 by rho z, it is h. P1 squared by 2z as it is. Z1 is 0. On the right hand side, P2 by rho z is h plus h. P2 squared by 2z is 0. Z2 is 0. So you will have h cancelled off. You will be having simply V1 squared is equal to 2gh, or V1 is equal to root 2gh. Again, this is a theoretical equation, right? This is theoretical velocity. Actual velocity will be slightly lesser. The multiplier, which will be showing that reduction in the velocity. So V1 actual is equal to CV root 2gh. This is called coefficient of velocity. Therefore, velocity at any point is given by CV root 2gh. H is, what is this h? H is a rise of the liquid in Pitot tube above the free surface. Okay.